Now we will start with our application development. For the developing of machine devices, we will use the so-called MVC programming style. You can check on YouTube how that programming style works. We will divide each machine part into these three objects. The model in our case are the inputs and outputs of the machine part. They will be inside a composite block called I/O. The control logic will be executed inside the controller, which will be also a composite, but called CTRL. All the visualization elements will be in the view, which is a cat, called Visu. Since we are also creating a digital twin, we will use a second model inside a composite object called Sim. And we will use a basic block for switching between the two models. So when we are in simulation mode, we will use the simulated I/Os, and if we are not in simulation mode, we will use the real I/Os. In this course, however, we will not have real I/Os. The controller is not aware if he is communicating with real I/Os or simulated ones. We will also have corresponding adapters for communication. The control block will communicate with the model through an I_IO adapter and with the Visu block through an I_Visu adapter. We will create the hopper first. Let's create a cat called HO. But let's organize our EAE project correctly. We will use folders for better organization. Let's create folders for each part of the machine. We create a folder for the injection unit called IU. We will create a folder for the mold unit called MU. And we will create a folder for the handling unit called HU. We will do this also on the composite level and on the basic block level. Now we will create the control logic block for the hopper as a composite object called HO_CTRL. We will create an additional cut for the hopper visualization. We will create the simulation algorithm of the hopper inside the basic block HO_sim_bub. For the simulation, we need a composite called HO_sim. Yes, I forgot the folders for the adapters. Let's create the I_IO adapter for the hopper called I_HO_IO. Let's clear the automatically generated variables and events. We will have a feedback event created by the IO block. These are our digital and analog inputs. Let's see, we will have analog level value, for example. Let's place the block inside our cat. Also the simulation block, the control block, the IO block, and the visualization block. We need the adapter between control block and visualization block. Let's place this adapter inside the visualization. We will place the Visu adapter as a socket and we will call it iControl, since the socket input connection will be connected to the control block. Let's save it. Let's do the I/O block 2. Here we add the I/O adapter as a plug called iControl. The same will be done for the SIM block. The control block will have sockets connected to the I/O blocks and a plug connected to the VISO block. Let's connect this. We will give the instances better names. We need the simulation switch block so we can switch between the I/O adapter and the SIM adapter. The switch will have two sockets for the I/O blocks and one plug for the control block. Let us create the code for the SIM switch. Save and place the SIM switch inside the hopper cat. Let's rename the SIM switch instance. This is our device structure we will use for each machine component. Now let's go to the SIM composite block. We only have the plug here for now. I see that the variable level is in cursive font. This means it is not attached to an event. During the course, this will happen often because I forget to do it immediately. Just drag and drop the variable to the FTB event and save. Let's place the simulation algorithm inside the hopper simulation composite. We also need the sim cyclic composite for the generation of cyclic events. We will need to initialize the sim cyclic block. For this, we will use the init adapter. Let's create cyclic events each 500 milliseconds. I don't like the order of the output events inside sim cyclic. Let's change this and save. Now it looks better. I will need to access the simulation variable for the simulation switch. That's why I will use an event output called eSim and the corresponding variable of type bool. I will need to pass the init adapter to other blocks inside the hopper cat. That's why I will create a plug called initO for this purpose. The cyclic event will trigger the simulation algorithm each 500 milliseconds. The simulation will of course give us some level value. Let's delete the init state and the init algorithm. Inside the request algorithm, we will create a random level value each event. For that, we need a random internal variable. We will use our function rnd_num for that. Level equals random number multiplied with 100. This way the level will be somewhere between 0% and 100%. Let's connect this to the plug, eye control. Inside our simulation switch, we must read the simulation value. We don't need the init part. The simulation switch will have two states. One is feedback and the other is command. If we get an input event from the I/O block for the sim block or the sim block, the feedback state will be entered. Let's rename the algorithm to feedback. Let's add the command algorithm. Inside feedback, we will check for the simulation value. If true, pass the simulation feedback variables to the control block. Otherwise, pass the I/O feedback variables to the control block. Save. The command state will be entered if a command event from the control block has been received through the iControl plug. Okay, that's wrong. I don't need the FTP event here. I need the command event. Let's go to the I_HO_IO adapter and place the command event with a corresponding command variable called refill command of type bool. Let's add the command algorithm to this state. Let's execute the iControl feedback event if the feedback algorithm has been executed. Let's now do the same at the command algorithm. Here we must separate between the iSim and the IIO adapter. We want only one of the two to be executed depending on the simulation value. We will here first execute both, but inside the algorithm we will sustain one of the two command events. First, we put both command events to false. Now, depending on the simulation value, we will pass the iControl adapter to the corresponding block. Now let's test it. Oops, the simulation value is not attached to the aSim event. Save and run the basic block in test mode. Simulation is off now. Let's trigger the feedback from iSim adapter. This should not be passed to the iControl adapter since we are not in simulation mode. Now we do the same with the IO adapter. This should be passed to the iControl adapter. Yes, the iControl has been triggered. Now we test with simulation on. Okay, the iControl was not triggered through the IO adapter. This is correct. We still have the previous value of 33. Now let's trigger the iSim adapter with the value of 22. And we see the iControl adapter has been triggered and we see the value of 22 inside the iControl level variable. Now let's test the other way. We trigger the iControl command event and let's see where it will be passed. If the simulation is off, it should be passed to the IO adapter. This is good. Refill command is not true. Why not? Yes, I forgot to connect the refill command to the corresponding command event. Let's test again. The refill command is passed correctly now. Very good. Let us continue with the hopper cat. We connect the simulation event and value with the hopper sim block. Let us go to the visualization now. Here we place the init adapter as a socket. Let's save. We connect the init plug. Let's rename the init instance block and assign priority and delay time. Now we need to pass the values from the control block to the visu block inside the control block. To display the level, we need to have it as an input. In order to create a visualization for the hopper, we need to place the IDs block inside the VisuCat. Let's connect everything. Add the hopper cat inside our system and map it to our resource. Let's see if we can deploy without errors. It's very good. Now let's add the level to the visu so we can see the value. We will use a vertical bar for that. Let us adjust the vertical bar a little bit. I like it this way. I want to make it wider. Now we must place the instance into our canvas. I don't see it yet. Why can't I see it? Yes, I have to place the Visu sub-instance of the object HO. There it is. I don't like that I always need to enter the user and password here in the login prompt. Let's get rid of that. There it is. Now we can activate the local HMI without the password prompt. Let's turn on the simulation. The level value is not changing. Let's see why. Okay, the simulation algorithm is not producing any value change. Why not? I forgot to initialize the R&D num value with something. Let's try again. So we have now a change of the level value each 500 milliseconds. If the simulation is off, the change stops. Now let's create the refill command of type bool. Save. Let's place the command inside our visualization. We also place a corresponding label. We want to pass now this variable to our adapter, but there is no value for that. Let's add this value inside the IHO Visu adapter. We will now do some changes inside the simulation algorithm. If the refill command is active, we will increase the level, and if you're not refilling, we will slowly reduce the level. Let's connect the command inside the control block. Let's deploy and test. Okay, that's not working properly. Ah yes, I forgot to connect the refill value to the adapter. This is still not working. The refill command is received properly. Let's check the code inside the basic block. Ah yes, here is the error. I need to add the level also. Very good. Actually, it's almost very good. We need to limit the level. It can't get more than 100% and it can't get below 0%. This is better now. Since the refilling has to be done automatically, let us implement some parameters which define how the refilling will be executed. These parameters should only become visible when needed. Therefore, we will add a faceplate called parameter. Let's add a prefix and a suffix. We will also need a button to call this faceplate. Call faceplate with mouse click. Let's reduce the decimal numbers. Let's see if the values are passed to the control block. Yes, they are. Now we want to refill only till the max value, and we also don't want the level to get lower than the min value. We will use a basic block for that. We will fill if the HMI command is set. and we will fill if the level is lower than min value. We will stop filling if level is above max level. Okay, something is wrong here. We are now in error halt. Oh, we have here an event loop. As soon as the simulation is turned on, the HO sim is sending a feedback event. The basic block produces a command event which enters the sim block. And so we have an infinite call of events. We have to unplug this event loop. Let's test again. Okay, we still get over 80%. I don't like this, but it seems to work a little bit better. Let's see if the automatic refill will take place. Yes, that's good. If we deploy, the value for min level and max level gets reset to 0. Let's change that by using persistent values. Change that here. Now we got a new event, load persistent data. This event should be executed after the init. Now we have better initialization values after each deploy. Let's draw the hopper a little bit nicer. Let us also add a refill feedback so we can see when it is being refilled. We will use an LED for that. We have to add this variable to the adapter. There must be, of course, a digital input inside the I/O adapter for that. We have to simulate the refilling correctly. Let's see if the refilling LED is controlled correctly. Not yet. Ah yes, I forgot to connect it to the adapter. Let's test again. Still not working. Okay, the refilling feedback is there. Okay, I didn't connect it to the HMI variable. Let's test again. It works. From time to time, we should create a new version and back up our current version of the project. Let me show you how to create a backup and a new version. I will first archive the current project. Now I will close the current project and open the archived one under a new folder. I will call it Injection Molding Machine version 02. After the unarchiving, we have to rename the solution also to Injection Molding Machine version 02. This way, we archived the version 01 and created a new project with the version 02. Our hopper is not yet done. We want the hopper to add new granules only when needed. For that, we will use a digital output which opens and shakes the hopper for like 3 seconds. I will call this command shake. The level of the hopper will be reduced only when the shaking is active. We need also a shake command inside the Visu. Let's implement the shake button and a label. For now, I will connect the HMI shake command directly to the I/O adapter. Because we created a new project, the HMI security is turned on again. Let's turn security off. Let's test the shake command. Looks good. Okay, we can now proceed with the injection.